Hey, welcome back, AP Calculus students. Today we're looking at 5.6 related rates. This is the last section in the first semester's work. So it's the culmination of all the derivative stuff we've been doing. Related rates is it's not necessarily harder than stuff we've been doing. It's just that we need to be very careful when we set up our problems and make sure that everything's in the right place and stuff like that. So let's kind of jump into it. It says the radius of a sphere is a differentiable function of t, and let v be the volume. Find an equation that relates dv dt and dr dt. So what's happening is the sphere is probably expanding or contracting over time. That's why we have that's why they want us to do it in terms of t, our derivative. So let's just set this up. So the first thing we know is that we're looking at a sphere. All right, so what we want to do is we want to write the equation for a sphere, the volume of a sphere. So volume equals 4/3 pi r cubed. So that's just the regular volume of a sphere from geometry. All right, so the first thing we did is write the equation for volume. Okay, the next step that we're gonna do, because they want us to write it in a form that relates dv dt and dr dt, is we're just gonna do the derivative with respect to t of this whole thing. So we're gonna do derivative with respect to t. All right, so notice there's no t's in here, right? We only have v's and r's. So what we need to remember when we do this is anytime we do our derivative, because there's no t's in here, we're gonna have to do the chain part with the respect to t part. So let's go ahead and do this. So the derivative of v with respect to t is just gonna be dv dt. 4/3, we don't have to worry about that. We don't have to worry about the pi because the pi is also a constant, but we're going to do the derivative of r cubed. So we're going to do 3r squared. And because we're not in, r is not a t, we have to make sure we chain that. So we have to do dr dt. Okay, so let's clean this up a little bit. So we have dv dt equals 3, and this divided by 3 can cancel because all one big multiplication. So we have 4 pi r squared dr dt, which interestingly enough is the formula for surface area, 4 pi r squared. Okay, as we get further into this, these rates here are going to be important because the derivative part, the chain part, is just the slope. Right, it's the derivative of the radius with respect to time, and the derivative of volume with respect to time. So as we move ahead, those numbers are going to help us to solve problems, and that's the related rates part of it, because these derivatives are technically going to be rates. Okay, let's try another one. Similarly, we're just setting these up. So it says the radius and height of a cone are differentiable functions of t, and let v be the volume. Find an equation that relates dv dt, dr dt, and dh dt. So let's see. We have some cone, right? The thing about cones though is whereas spheres we just had the radius, and we could determine the volume by the radius. For a cone, we need to know the height and the radius, and this is going to come into play next time when we do conical water tank stuff. But so our volume for a cone is going to be 1/3 pi r squared h. So we have 3 different variables, right? We have our v, we have our r, and our h. So let's go ahead and do the same thing. So this was step 1, right? We write the equation Okay. Now step 2, we're going to go and derive with respect to t. Alright, so again we have dv dt equals 1/3, not affected by derivatives, neither is pi. But what we have here, I'm going to put parentheses here, is we have a product rule, right? Because we have the r squared times the h. So let's change colors one more time. I'll do it over here just because we have room. So we'll say u is r squared, du is going to be 2r. And again, because we're doing it with respect to t, we have to make sure we do dr dt. Then we have our v, which is the h. And then the dv would be dh dt. Okay, so let's put this all together. U dv is r squared dh dt plus v du 2hr running out of room. 2hr d whoops d v dr dt. Okay, so this would be our equation. Technically, I guess you could distribute the 1/3 pi, but I don't think it really matters that much. You could leave it like this. Okay, so let's actually apply this. So the example says a hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's angle is pi over 4. The angle is increasing at 0.14 radians per minute. How fast is the balloon rising at that moment? So we're being given a lot of information here, right? So, well, here's the balloon, right? And it's going up. Here's the person with the rangefinder, or the rangefinder itself. We know that the distance between the rangefinder and where it lifted off from was 500 feet. They're not giving us the height, but height is involved because we're trying to find how fast the balloon is rising. And we have our angle theta, right? Because we're doing angles and radians per minute. So let's set this up. The mistake here would be to think that we could do Pythagorean theorem because we're being given an angle. We want to use our trig functions. So if we're setting this up properly, we're going to look at the opposite, and 500 is the adjacent. So we're going to set up a tangent for this one. So we're going to say tangent theta is going to be the opposite over adjacent. So h over 500. Okay, so that's step 1, right? We set up our equation just like we did earlier. Step 2 is we're going to derive it, but before we derive it, let's make this a little bit neater. Let's multiply by 500 on both sides because we're looking for h, right? So we'll just leave h here. Okay, and then we'll do the derivative of both sides with respect to t. So what's happening in this situation as time is passing, right? The angle is increasing because the balloon is going up, and also the balloon's height is increasing. Okay, so when we do the derivative here, 500 tangent theta, the 500 is unchanged, but the derivative of tangent is secant squared theta. And then we're going to do d theta dt, right? Because we have that variable theta in there. And then the right hand side is just going to be dh dt. Okay, so that's step 2. And then step 3 is we're going to plug in all our applicable information. So let's see what's going on here. So we have 500. Then we have secant squared. Now we know what our theta is. We have secant theta, which is pi over 4. Right? At the moment that the angle is pi over 4, the rate of change, right? They said the change is 0.14 radians per minute. So 0.14. And that's going to give us dH dt. And luckily enough, dH dt, well, that's the change in height over time, right? So how fast is it rising? That's exactly what we're looking for. We're looking for the rate of change of the height with respect to time. Okay, so all we have to do is put this in our calculator. The only weird thing is that we can't do secant squared square root of 4. In our calculator, we'd have to do 1 over cosine pi over 4 squared. Okay, so just make sure that when we do it on our calculator, you do that. So then we get 2. Does that make sense? Cosine of pi over 4 square root of 2 over 2 squared is going to be square root of 4 over 4, which is 2/4, 1/2. Reciprocal is 2. Okay, excellent. So it's 2, kind of running out of room here. But what we have is 500 secant squared pi over 4 is times 2 times 0.14, and that should give us our change in height with respect to time. So let's do that. 500 times 2 times 0.14 is 140, and this is going to be in feet per minute. So I guess 140 feet per minute is not very fast, right? It's like 2 feet about per second. Yeah, it's not too bad. It's slowly lifting off the ground. Okay, that is it for today. Just trying to get our feet wet with this related rate stuff. So again, we start off with writing the appropriate equation down. Then step 2 is doing our derivative with respect to t, remembering to do all the chains for all the different variables. And then lastly, we're just going to plug in all our information and hopefully it comes out nicely. All right, good job.